Time travel. The very words spark our imagination. Journeying to the past, witnessing history firsthand, or leaping into the future, a world transformed. Is it merely fantasy, or could science unlock the secrets of time itself? For centuries, this question has fascinated humankind, fueling countless stories and captivating our dreams. What if I told you that time travel isn't just a whimsical notion confined to the pages of science fiction? What if I told you that it's a concept rooted in the very fabric of our universe, governed by laws of physics we are only beginning to comprehend? The journey to understanding time travel begins with a deep dive into the mind of a genius, a man who revolutionized our understanding of space, time, and the cosmos, Albert Einstein. Einstein's groundbreaking theories of relativity, first unveiled in the early 20th century, provided the first tantalizing hints that time travel might be more than just a flight of fancy. His work challenged our intuitive understanding of time as a rigid, unchanging constant, revealing instead a universe where time is fluid, malleable, and intimately intertwined with space. In the sections that follow, we'll embark on an exhilarating exploration of time travel, delving into the mind-bending concepts of relativity, exploring the potential pathways and pitfalls, and pondering the profound implications of manipulating the very essence of existence. Buckle up, fellow travelers, as we embark on this cosmic adventure. Imagine this. You're racing alongside a beam of light, trying to catch up. Seems impossible, right? Light, after all, travels at the fastest speed imaginable, a staggering 299,792,458 meters per second. Einstein, however, dared to ask, what if we could approach the speed of light? What would we observe? His answer, enshrined in his theory of special relativity, shattered the very foundation of classical physics. Einstein revealed that time is not absolute, but relative. The faster you move through space, the slower time flows for you relative to someone standing still. This mind-boggling concept, known as time dilation, has been experimentally confirmed time and time again. One compelling example is found in the behavior of muons, subatomic particles that rain down on Earth from the upper atmosphere. Muons have a very short lifespan, decaying quickly after they are created. However, because they travel at nearly the speed of light, time dilation causes their lifespans to appear much longer from our perspective on Earth. They actually reach the ground, defying our classical understanding of their fleeting existence. This phenomenon of time dilation isn't just a scientific curiosity, it has real-world implications. For instance, the GPS satellites orbiting our planet rely on incredibly precise timekeeping. However, because they're moving at high speeds in Earth's gravitational field, they experience time slightly differently than we do on the surface. To ensure accurate positioning, engineers must account for these relativistic effects. Special relativity introduced us to the mind-bending concept of time dilation, demonstrating that time is not a constant but rather a variable dependent on speed. However, Einstein didn't stop there. He went on to develop his theory of general relativity, which unveiled an even more profound connection between gravity and time. General relativity postulates that gravity isn't simply a force but rather a curvature of space-time, the very fabric of the universe. Massive objects like stars and planets create distortions in space-time, much like a bowling ball placed on a trampoline stretches the fabric around it. This curvature of space-time affects not only the trajectory of objects but also the flow of time. Time slows down in stronger gravitational fields, meaning that time passes slightly slower at sea level than it does on a mountaintop, where the gravitational pull is weaker. Again, this effect has been experimentally verified, solidifying general relativity as one of the most successful theories in physics. Imagine time as a river, flowing relentlessly from the past to the future. Einstein's theories of relativity suggest that this river isn't a uniform, straight channel. Instead, it meanders and curves, its flow influenced by the presence of massive objects and the speed of travelers. Just as a river's current can change, speeding up in narrow passages and slowing down in wider stretches, so too can the flow of time be affected by the fabric of space-time itself. But what if we could do more than just navigate the currents of this cosmic river? What if we could find a way to cheat the system, to paddle upstream against the flow of time itself? This is where the concept of time travel becomes truly tantalizing, pushing the boundaries of our understanding and challenging us to imagine the seemingly impossible. While the idea of time travel might seem like pure science fiction, it has captured the imaginations of physicists and laypeople alike for decades. From the whimsical time-turner in the Harry Potter series to the iconic DeLorean in Back to the Future, our cultural fascination with time travel reflects a deep-seated desire to explore the uncharted territories of the past and future. But could such journeys ever be possible outside the realm of fiction? Let's delve into the scientific concepts that might hold the key to unlocking the secrets of time travel. Section 5. Warping the fabric. Einstein's theories of relativity provide the theoretical framework for understanding how time travel might be possible. But the practical challenges are immense. One of the most intriguing concepts involves manipulating the very fabric of space-time itself, a concept known as wormholes. Imagine a piece of paper representing space-time. Now fold the paper in half so that two distant points touch. A wormhole, theoretically, acts as a shortcut through space-time, connecting those 2 points and allowing for instantaneous travel between them. While this might sound like something straight out of Star Trek, the mathematics of Einstein's equations do allow for the possibility of such space-time shortcuts. However, creating and stabilizing a wormhole presents monumental challenges. Wormholes are thought to be incredibly unstable and require exotic matter with negative mass-energy density to prop them open. This exotic matter, while theoretically possible, has never been observed, and its properties remain shrouded in mystery. Despite the immense hurdles, the concept of wormholes continues to captivate the imaginations of physicists, offering a tantalizing glimpse into the potential for traversing vast cosmic distances and perhaps even journeying through time itself. Section 6. Around and through the wormhole. While wormholes remain highly speculative, they represent just one potential avenue for time travel. Another intriguing possibility arises from the concept of rotating black holes. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. According to general relativity, a rotating black hole can create a sort of cosmic whirlpool, dragging space-time along with it. This space-time distortion could, theoretically, create closed, time-like curves, pathways that loop back on themselves, allowing for travel through time. Imagine yourself caught in the flow of a powerful whirlpool. As you're dragged around and around, you might eventually find yourself back at a point you've already passed. Similarly, in the vicinity of a rotating black hole, the fabric of time itself could be twisted and contorted, potentially allowing for journeys into the past or future. However, navigating the extreme gravitational forces and avoiding the singularity at the heart of a black hole pose formidable, perhaps insurmountable, challenges. Moreover, the very act of entering a black hole is thought to be a one-way trip, making a return journey highly unlikely. Section 7. Tiny victories, gigantic leaps. While the prospect of building a time machine or traversing wormholes might seem like a distant dream, scientists have made remarkable progress in understanding the fundamental nature of time and its relationship to the cosmos. Experiments have repeatedly confirmed the predictions of Einstein's theories, demonstrating that time is not the absolute, unchanging constant we once believed it to be. One groundbreaking experiment involved flying atomic clocks aboard jets, demonstrating that time passes slightly slower at high altitudes due to the weaker gravitational pull. These minuscule time differences, while seemingly insignificant, provided compelling evidence for Einstein's theory of general relativity. While these experiments might not allow us to hop into a DeLorean and visit the dinosaurs, they represent crucial steps towards unraveling the mysteries of time. Each tiny victory, each experimental confirmation, brings us closer to understanding the fundamental laws governing our universe, and the tantalizing possibility of manipulating time itself. Section 8. Paradoxes and possibilities. The prospect of time travel raises a host of fascinating paradoxes, challenging our understanding of cause and effect. One of the most famous is the grandfather paradox. Imagine traveling back in time and accidentally killing your grandfather before your parent was born. If your grandfather died, you would never have been born, but if you were never born, you couldn't have traveled back in time to kill your grandfather. This paradox highlights the potential for logical inconsistencies when tampering with the past. Physicists have proposed various solutions to these paradoxes. One possibility is the Novikov self-consistency principle, which suggests that any actions taken by time travelers are already woven into the fabric of space-time, ensuring that paradoxes cannot occur. In other words, if you were to travel back in time, you would be prevented from taking any actions that would alter the past in a way that contradicts the present. Another possibility is the existence of parallel universes or alternate timelines. Perhaps every time a choice is made, a new timeline branches off, creating an infinite number of parallel universes, each with its own unique history. In this scenario, time travel might involve hopping between these alternate timelines rather than altering a single, fixed past. Section 9. The Undiscovered Country. Time travel remains one of the most captivating and enduring mysteries of the cosmos. While the practical challenges of building a time machine or traversing wormholes are immense, the very possibility continues to fuel our imaginations and inspire scientific exploration. Will we one day unlock the secrets of time, unraveling the mysteries of the past and charting the uncharted territories of the future? Only time will tell. Perhaps our descendants will look back on our era as a time when the concept of time travel was still in its infancy, a time when the true potential of this mind-bending concept was just beginning to be explored. As we continue to probe the depths of the cosmos and unravel the fundamental laws governing our universe, one thing remains certain: the journey of scientific discovery is just as exhilarating as the destination. Whether time travel ultimately proves to be a scientific reality or an enduring fantasy, the pursuit of this extraordinary concept will undoubtedly lead to profound insights and unimaginable breakthroughs, shaping our understanding of the universe and our place within it for generations to come.